The leakage current that flows through condensate in this scenario is typically a high-frequency alternating current due to the capacitive coupling between the hot conductor and the grounded bathroom fixtures and appliances. The frequency of the leakage current is typically in the range of 10 kHz to 30 kHz, which is the operating frequency of commonly used blow dryers. The magnitude of the leakage current depends on several factors, including firstly, the distance between the hot conductor and the condensate, secondly, the area of the surface coated with condensate, thirdly, the conductivity of the condensate, and fourthly, the voltage on the hot conductor. Typical leakage currents in this scenario range from a few milliamperes to several tens of milliamperes. A ground fault circuit interrupter is a safety device designed to detect leakage currents to ground and trip to interrupt the circuit in the event of a hazardous level of leakage current. In this scenario, the ground fault circuit interrupter is unlikely to trip due to the following reasons. 1. High-frequency leakage current. Ground fault circuit interrupters are typically designed to respond to low-frequency leakage currents, typically 50 or 60 Hz. High-frequency leakage currents may not be detected by the ground fault circuit interrupter. 2. Low magnitude of leakage current. The magnitude of the leakage current in this scenario is typically below the trip threshold of most ground fault circuit interrupters. Let's delve into the specifics of leakage current in this scenario. We'll explore the nature of the alternating current and why the frequency is significant, as well as the factors that influence the magnitude of the leakage. Finally, we'll discuss why a ground fault circuit interrupter might not respond as expected. Leakage current, in this context, refers to the unintended flow of electrical current from a conductor, specifically the hot conductor of the blow dryer, to ground through an unintended path, which is the condensate layer on the bathroom surfaces. Condensate is water that has condensed from a gas to a liquid, in this case from the steam of the shower. The characteristic of the leakage current is that it's a high-frequency alternating current. Alternating current means that the direction of the current flow reverses periodically. The frequency refers to the number of times this reversal occurs per second, measured in Hz. The typical household alternating current frequency is 60 Hz in North America. However, in this situation, the frequency is significantly higher, ranging from 10 kHz to 30 kHz, which is the operating frequency of the blow dryer. This high frequency is crucial because it affects how the current interacts with the environment and how it's detected by safety devices. The high frequency of the alternating current is due to what's called capacitive coupling. Capacitive coupling occurs when two conductors are separated by an insulator, in this case, a hot conductor and the grounded bathroom fixtures, with the condensate acting as a dielectric material between them. This arrangement forms a capacitor, which allows alternating current to flow through it even though there is no direct electrical connection. At higher frequencies, the impedance, which is the opposition to the flow of alternating current of this capacitor, decreases, allowing more current to flow. The magnitude of the leakage current, or how much current flows, depends on several key factors. Firstly, the distance between the hot conductor and the condensate is crucial. The closer the conductor is to the condensate, the stronger the capacitive coupling and the higher the leakage current. This is because the electric field between the conductors is stronger when they are closer. Secondly, the area of the surface coated with condensate matters. A larger surface area means more contact between the condensate and the electrical field, leading to a higher leakage current. Thirdly, the conductivity of the condensate is significant. Pure water is a poor conductor of electricity. However, bathroom condensate typically contains impurities such as soap, shampoo, and minerals from tap water, which increase its conductivity. Higher conductivity allows more current to flow through the condensate. Finally, the voltage on the hot conductor is a direct factor. Higher voltage drives more current through the leakage path. In typical household circuits, the voltage is around 120 volts. Given these factors, typical leakage currents in this scenario range from a few milliamperes to several tens of milliamperes. Now let's discuss the ground fault circuit interrupter operation. A ground fault circuit interrupter is a safety device designed to protect against electrical shock by detecting leakage currents to ground. It works by monitoring the current flowing through the hot and neutral conductors of a circuit. Under normal conditions, these currents are equal. If a leakage current occurs, meaning some current is flowing to ground through an unintended path, the current balance is disrupted. When the leakage current exceeds a certain threshold, typically 5 mA, the ground fault circuit interrupter trips, quickly interrupting the circuit and preventing electrical shock. However, in the case of high-frequency leakage currents flowing through bathroom condensate, the ground fault circuit interrupter may not trip as expected, and this is due to a couple of reasons. One reason is the high-frequency leakage current itself. Ground fault circuit interrupters are typically designed to respond to low-frequency leakage currents, typically 50 or 60 Hz, which is the standard frequency of household alternating current. The internal circuitry of a ground fault circuit interrupter may not be sensitive to high-frequency currents or may filter them out, preventing the ground fault circuit interrupter from detecting the leakage. This is because the inductive reactance of components within the ground fault circuit interrupter increases with frequency, effectively blocking the high-frequency current. Another reason is the low magnitude of the leakage current. While the leakage current in this scenario can be a few milliamperes to several tens of milliamperes, it may still be below the trip threshold of the ground fault circuit interrupter. Most ground fault circuit interrupters have a trip threshold of 5 milliamperes, but there is some tolerance and variation in this threshold. If the leakage current is consistently below this threshold, the ground fault circuit interrupter will not trip, even though there is a leakage path present. Now let's discuss some practical considerations. Firstly, it's important to note that even if the ground fault circuit interrupter doesn't trip, a leakage current can still pose a risk. While the current may not be high enough to cause immediate electrical shock, prolonged exposure to even low levels of leakage current can be harmful. Secondly, the presence of condensate in a bathroom is a common occurrence, and it's difficult to completely eliminate it. Therefore, it's essential to take precautions to minimize the risk of leakage currents. Thirdly, it's recommended to use ground fault circuit interrupter outlets in bathrooms and other areas where water is present. While ground fault circuit interrupters may not always trip in the presence of high-frequency leakage currents, they still provide valuable protection against low-frequency ground faults. Here are some recommendations for minimizing the risk of leakage currents in bathrooms. Firstly, ensure that all electrical appliances used in the bathroom are in good condition and properly grounded. Check the cords and plugs for any damage, and replace them if necessary. Secondly, avoid leaving electrical appliances plugged in when they are not in use. Even when an appliance is turned off, it can still draw a small amount of current and contribute to leakage. Thirdly, keep electrical appliances away from water sources as much as possible. Do not place them near sinks, showers, or bathtubs where they could come into contact with water. Fourthly, regularly clean bathroom surfaces to remove condensate and other contaminants. This will help to reduce the conductivity of the leakage path. Fifthly, consider using a dehumidifier in the bathroom to reduce the amount of moisture in the air. This can help to prevent the formation of condensate on surfaces. Sixthly, if you suspect a leakage current, do not attempt to diagnose or repair the problem yourself. Contact a qualified electrician to inspect the electrical system and make any necessary repairs. Regarding high-frequency ground faults, these can occur due to a variety of factors, including switching power supplies, electronic ballasts, and variable frequency drives. These devices generate high-frequency noise that can couple to ground and create leakage currents. Electrostatic discharge in power distribution systems is another related phenomenon. Electrostatic discharge can occur when there is a buildup of static electricity on a surface, which can then discharge to ground through a conductive path. This discharge can create a high-frequency transient current that can also cause leakage. In summary, the leakage current that flows through condensate in a bathroom setting is typically a high-frequency alternating current. The magnitude of the leakage current depends on several factors, including the distance between the hot conductor and the condensate, the area of the surface coated with condensate, the conductivity of the condensate, and the voltage on the hot conductor. A ground fault circuit interrupter may not trip in this scenario due to the high frequency nature of the leakage current and the low magnitude of the leakage current. It's essential to take precautions to minimize the risk of leakage currents in bathrooms, such as ensuring that all electrical appliances are in good condition, avoiding leaving appliances plugged in when not in use, keeping appliances away from water sources, and regularly cleaning bathroom surfaces.